Fraud proofs are broken, but we can fix them. This is the title of a recent blog post on the Ethereum research forums authored by Gabriel from the Cartesi Foundation. In this video, we talk with Gabriel about his research, the current Optimism and Arbitrum implementations of fraud proofs, as well as Cartesi's permissionless refereed tournaments. This post and this video is a call for collaboration so that the entire Ethereum community can rally around interactive, permissionless fraud proofs. Please enjoy this video. GM, what is going on? Today we are here with Gabriel, core developer of Cartesi, and today we're going to be talking about something that is long awaited in this ecosystem. There's been a lot of conversation, all purely theoretical, and hopefully as a result of this conversation we can get a little bit more practical with the application of fraud proofs. I'm gonna leave the explanation of fraud proofs to Gabriel here in a minute. But first, Gabriel, welcome to the Rollup, and it's a pleasure to have you on. Maybe you could start by introducing yourself. Tell us a little bit of your journey that brought you up to being a core developer at Cartesi, who specializes in the Linux VM. What brought you to this point in your research?
Yeah. So hello, thank you for having me. So I joined Cartesi on 2020. I think the pandemic had just started, and I was in the middle of my master's degree. A friend of mine who actually he has been here, Felipe, he invited me to join Cartesi, and I did. So I've actually worked on many parts of the overall stack. And right now, I'm specifically working on the fraud proof system, which is the topic of today.
Awesome. Okay, so let's start high level. It's obviously some sort of proof, right? A fraud proof. But what is a fraud proof?
Yes. So I think first we have to set the context, and the context is scalability. We want to scale Ethereum. And we want to do that without compromising on security or decentralization. Because we can naively increase scalability of Ethereum, but sacrificing the other two. So we need to get smart if we want to get all of the three of them together. And as you know, the solution proposed that the ecosystem is going to is Rollups. And the idea is that you are going to execute everything off-chain. So you are kind of like making the Ethereum base layer requiring less compute because you're moving compute away and you're doing it off-chain. And then you're using some sort of proof system to prove back to Ethereum that the result of all this compute that you did is correct. So this is where the fraud proof come in. It's actually addressing this. Let's add more scalability, more block space without actually changing the base layer. And the way the fraud proofs work, it's actually quite different than, there are two main proofs that we talk about today, which are ZK proofs validity proofs and fraud proofs. And the main way fraud proofs work is that you actually have a set of validators who are all together validating the rollup. They're running all this off-chain compute together. And as long as a single one of those validators is honest, you can enforce the correct result. So those are the guarantees that fraud proof give you. And we, on that lens, if it requires only a single honest validator and you can participate on that validator set, then we can, argue quite well that we are inheriting the security of Ethereum. If you care about some rollup, all you have to do is set up, a laptop to validate, and you're honest, and you alone are capable of enforcing the correct result. You don't need to trust anybody else. So that's the overall idea of how fraud proofs, like the mechanism is. But the underlying assumption is that you need this validator set participating to be permissionless. You must allow anyone to join in. And it turns out it's very hard to design good algorithms that are both one of n. We call this single honest validator in a set of n validators as one of n is like the way we call this property. So it's very hard to keep the one of n, keep the permissionless, also allow it to be like cheap, like you don't want to have like a supercomputer or requiring like huge stakes or bonds, and also settling quickly. So trying to fit all of those together is actually quite hard. You end up sacrificing one or the other or more than one. And that was the context of that whole article that we're going to talk about today. Because we all, I mean like the ecosystem, like Arbitrum, Optimism, Cartesi, and others, we've seen this problem, and we have proposed algorithms that try to address all these problems. But our analysis is that none of them are actually good enough. There was a recent article by Vitalik where he says the ecosystem standards needs to become stricter. And that's absolutely true. I think we can do better on fraud proofs. And that whole article is actually a call for collaboration. We offer a criticism, like we analyze and criticize all solutions, including ours, and try to invite in everybody for us together to figure out something good. Because I think some of these might not have even, maybe we didn't even realize we had those problems. And the first step is like, look, we have this, depending on the algorithm, different issues, and we need to address them and try to open up the stage where we can do that together.
Yeah, and fraud proofs are a bit of a contentious subject in the field of rollups at the moment. I think there's been this call for fraud proofs for quite a long time, and everyone is sort of fighting to be either the first or the best solution to that problem, and it leads to a lot of infighting. Whereas a lot of this is just a benefit to the end user. If we can end up with the quickest, best solution, everyone wins. So I love the perspective of basically this article that we'll screen share and we'll go through in a moment. Is basically a call for collaboration. And to get some different criticisms on both sides so that we can constructively find the best solution to this fraud-proof problem. We're going to say fraud proofs a lot
Yes.
during this video. Okay. You also mentioned an article by Vitalik. I just want to highlight that article. What was that one called so that the audience can
It's the latest one. Maybe there's another latest one. So I think it's the we have blobs. What now? I think that's the one. Yeah.
Awesome.
So yeah.
Cool. So we'll I'm gonna bookmark that in my mind too because I want to check that one out afterwards. Okay, great. So you mentioned a couple things that I want to talk about high level before we dive into the nitty gritty of the research post. So you mentioned 3 different categories of proofs: validity proofs, ZK proofs, and fraud proofs.
Yes, I was actually bunching ZK and validity together, because ZK proof is like a proof that the whole computation is valid. And that's in contrast with fraud proofs because you prove that the computation is invalid. That's why you need a host of validators, because the single honest one, that's the curious behavior of the algorithm. It doesn't actually find the truth. It actually doesn't even find lies, it finds liars. So what you do is you're the single honest validator. That's the worst case scenario. You can prove that everybody else is lying. There is this interactive process you go through, and you essentially you can catch these liars in a contradiction, So the blockchain kind of goes asking questions. The blockchain acts like this referee, so it asks you, the honest one, like, what was the state at that specific point, and then it asks the dishonest party, and until it reaches a certain point where it can kind of catch this disagreement, this divergence, and then eliminate the liar. So you're not actually proving that yours is true. You're proving that the other is a liar, and if we assume that there's one honest person, that honest person will survive, and then you can enforce the truth. So it's actually inverted.
Got it. So I think that starts to answer my second question, which was, how do we know if 99 of the validators agree and I disagree and I'm the honest one? How do I know? How does the blockchain know that what 99% of the consensus is actually the thing that's wrong, and it's my minority opinion or my minority validation that is the honest one? When you start,
Yes.
you start to answer that.
Yes, I will. So this is, I need to zoom in actually, because this is interactive fraud proofs. There are non-interactive fraud proofs, and that paper doesn't talk at all about non-interactive, it's just interactive. So I'll explain how this interactive works. So all the communication happens on-chain. There is no communication between the set of validators happening off-chain. If we talk, is mediated by Ethereum. So what happens is you have an epoch, if you're considering rollups. We can actually reduce the problem to just being a computation. It's easier to reason about instead of a rollup. You can think of a rollup as being like computations chained together, and this chaining interval happens at the end of every epoch is when you settle. So let's think of just a computation. It's going to be easier. So the setup is, considering only two parties, the setup between two parties is that we both agree on an initial state and a state transition function. So this initial state, for example, if we are playing, I don't know, chess, the initial state is going to be the chessboard and the rules of chess. And if we want to play chess, we need to at least agree on that. So we agree on that, and there's the state transition function. I guess maybe you could think of the state transition function as being the logic of the chess itself, or in our case it's easier, it's just a virtual machine, and then you implement the logic on top of that. And the state transition, on our case, is RISC-V. It's like a single RISC-V CPU tick, single instruction. You could also do WebAssembly, you could also do EVM, you could do MIPS. It's curious because Arbitrum and Optimism, they are EVM, but the underlying machine is actually MIPS and WASM. You can, anyway, so you agree on those two things, the state transition and the initial state. For you to reach the final state, what you do is you apply the state transition function iteratively. So in the loop, you just go and do the state transition. You keep doing that until the computation is done, until you prove that, on the chess game that, not prove, but until you reach the end of the chess game, checkmate.
Mm-hmm.
And once you reach the end of that, you go back to the blockchain and you say, this is the final state. So that's a claim. That's a proposal of the result of running this whole computation. And once I make this claim, you will also make this claim. If the two claims are the same, the system will optimistically assume that it is correct. But if there's a divergence, like I say something, you say something different, then somebody has to be lying, and you start a fraud proof process where one of us will prove that the other is lying. And the process if you want to, do you want to know like the in-depth mechanism?
Yeah, I think so. I think I love the analogy of the chess game, the initial state, the state transitions of playing chess, and then and each move on the chessboard is a state transition. Ultimately, we reach the end of the chess game, which is the end of the epoch. Right, is when we would
Yes.
settle the winner of the chess match to Ethereum, or the final state of the chessboard even to Ethereum, and then
Exactly.
the one thing I wanted to clarify is that in the chess match example, there's two validators, correct? And if these validators agree, optimistic settlement, everything's cool, truth. But if these two players disagree, that's when we start the prod proof example. Now, extrapolate this to the Ethereum world. We don't have two players. We have N validators, N players, correct? And if all N validators agree, optimistic settlement, everything's good. But if 1 out of N or 2 out of N or some amount out of N validators disagree, then because there's some disagreement, we must start this fraud proof resolution mechanism.
Yes, exactly. So
Okay.
that's a perfect observation that the chess example, it's quite well behaved because it's just two players. So it's just two people interested that have a stake on the result of the computation.
Mhm.
It's like, suppose I win, but you say that you win. Like, it's on my best interest to try to prove you wrong, and vice versa, you know? So it's perfectly aligned that every user of the rollup is the validator. So it's just two players, it works well. But when you extrapolate it to Ethereum, where you have something like a DEX, or actually a full EVM rollup, or something that anyone can participate, then the validator set and the users kind of like start diverging. So you have to separate those two, and you have to guarantee that, not guarantee, but well, you assume that at least one of them is honest. You might want to have some incentive to make sure that people want to be honest. But this is like outside the fraud proof system itself. The fraud proof is kind of like just a primitive. So the way you expand the two player to n player, it's actually, there are many ways of doing that. So I guess the two most straightforward ways are, first, you match everybody in pairs. Everybody that has a different, who disagree, in pairs, and then you can eliminate the liars, and then you pair them again, and then you eliminate the liars, and you pair them again until all the participants who remain, they all agree. Then there's the other one where you kind of pair everybody with everyone at the same time, and then you fight, like each one fights n matches at the same time, or n minus one, I guess. Anyway, so you can just fight everybody at the same time. And both those approaches, or either of those approaches, they don't scale well on the number of players. Because if you make it so that every validator fights at most one validator, that's the first alternative. So you pair everybody, like in pairs, really. So you're only fighting one at the same time. If you do that, then the settlement is delayed a lot. Because on the worst case scenario, you will have to fight serially n matches, and the match can take 1 week. And if there are like 50 players, 52, then it's already taking a year. So that's like a delay attack. You can just go there, like the adversary, they can create 50 fake personas. They burn stakes to do that. That's not a problem, like obviously depending on the value, but they can delay things for 1 year, and that's not good. That's, as I said, we need to become stricter. this is terrible. We all realize that, and that's where this whole wave of new algorithms emerged from. And the other way, which is everybody fights everybody at the same time, it's also not Sybil resistant, because you need to have enough resources to fight everybody at the same time in a way that you wouldn't need to have if it's like in series. So this initial idea of fraud proofs, which is based on this two-player primitive, it works quite well if you have like maybe 100 people, like validators. If you have a permissionless of validators, you can make that work. But then it's hard to argue that that is safe, because I want to be able to participate and ensure the safety of the whole thing, because it's one of n. But if one of n means one of 50, it's not good enough, It's certainly better than a multi-sig. It's certainly better than, like it's acceptable as this intermediary state where we have like a permission set of validators and we're working on the permissionless set. But we need to keep researching an algorithm that will work with all these criteria that we're interested in.
Okay, so that there's a lot to unpack there. I want to start with a question because the chess example is very, very easy. I think I understand the chess example, and then extrapolating that to more than two validators is increasing difficulty quite quickly. So one question I have is that we have a couple parameters in the chess example. We have two players, and we only have two outcomes for each player, depending on what we're settling back to Ethereum and for this chess game. When we're settling the winner and the loser, there's only two outcomes for the it's just, they're agreeing on a win or a loss. If we are then so I want to just start with the chess example again. Yes. Are we settling the chess winner and loser back to Ethereum, or are we settling the array of the chess pieces on the chess board? Because if it's the latter, if it's the chess pieces on the chess board, there's so many different combinations that people could agree or disagree about. And so that gets much, much more complex than just settling the winners and the losers, because that's only binary and it's much more simple. There's only so many things that we could disagree about. But if we're talking about the chess pieces, there's so many combinations of different chess pieces on the chess board. And so if we have 50 people that are validating the configuration of the chess pieces on the board, it's possible that all 50 validators have a different perspective and settle something different. They have a different configuration that they settle back to Ethereum. We have 50 different disagreements. If we're just doing the winner and the loser, maybe 25 people say that this person won, the other 25 say that person won. So how do we handle the situation where there's not just an agreement and a disagreement, but there's agreement, disagreement, and then a third or fourth or fifth or sixth perspective on what happened?
Yes. So that's like a perfect question. You don't settle the winner versus loser. You actually have to settle the chess board, the whole configuration of the pieces. Otherwise, you won't be able to do the dispute process, because dispute works on the chess board configuration. So like you have the initial configuration and the final configuration, and then you claim that configuration you won, and the way the algorithm works, it will ask just to person, just to validators. It will ask, what was the configuration in the middle? And if they both agree, it means that they're disagreeing on the configuration on the second half of the game. And if they agree on the middle point, it means that they're disagreeing on the first half of the game. So you kind of go like reducing, cutting the search space in half until you find two board configurations where before both players agree and after they disagree. And that's where the blockchain applies the state transition function once and says, no, look, if you agree on this configuration, I know that the next configuration is A, and you said it's B, so you have to be lying. Now, if you have, as you said, you could have like 50 validators, and each one is actually claiming a different thing. So let's assume there is one honest validator. That's the assumption. Because if we don't assume that, all the 50 ones can actually be untrue. But if we assume that there's one honest validator, one of them is true. So, like naively, what you can do is you could have the honest validator fighting the first dishonest and then proving he's lying. It then goes to the second one, proves that he's lying. And it keeps going through all 49 liars and eliminate all of them. And since it's now only one opinion left, that one has to be the truth, because we assume there's one honest validator. There are different ways where you can set up this matchmaking. You can kind of like match everybody together with everyone. So the honest one would simultaneously be fighting all 49 of them. And each of the 49 would also simultaneously be fighting the other 49. And this is fast, because like by the end of the week, there's only going to be one surviving. But then it's very intensive on resources. So there's this trade-off. Mm-hmm. But the approach is this: you kind of like match validators together in this two-player setup. And one of them will be proved to be lying. But you did raise a very interesting point. Like, what happens if it's like 25 say one thing, the other 25 say another? And the curious thing is that if you take the setup that you fight in series and not at the same time, the optimal strategy for delays is actually 49 correct results, correct claims, one incorrect claim. However, only one of the 49 was made by an honest validator. Just reiterate what I said before.
Can I make sure? I think I understand. I just want to make sure. So you're saying that you have the bad fight the bad, eliminate each other, and then you just get all the way down to the one honest one and have them eliminate the the best villain in a sense.
Yes, exactly. So that is like a tournament, like with brackets approach, and that's like our algorithm, like the one we proposed. Actually does this. This is the approach. You have like the good one fighting the bad one, but all the other bad ones fighting each other. Yeah. Then you kind of like go fighting on the brackets. Right. But to enable that, we needed to make a core shift on how the overall disputes work. And this shift, it's very subtle, but it has to do with this. Somebody can say the right result. They can post the correct chess configuration, but then lose on purpose. There is a way for them to lie during this, what was the configuration in the middle? And they can lie. They can say, no, it was something completely. So they said the correct final one, but they play the game dishonestly and they lose on purpose. So if you just witness, you have 50 validators. If you just witness a single match, a single two-player match, you can't know what was the truth, because both could be lying, or one could be lying, another telling the truth, but the one telling the truth lost on purpose. So that's like the very fragile, this very annoying fragility of this two-player primitive. So there's this post that that Arbitrum made, which is the post that announced they were building Bold. The name hadn't been like released on that post. And the attack that the current Arbitrum setup suffers from is this. The adversary posts a single dishonest claim, and then he posts like 100 honest ones. And if they can control the matchmaking, they can make sure they are just fighting themselves one at a time and making the honest claim lose on purpose. So it's kind of like the honest one that is able to eliminate the dishonest one is actually just waiting like this, waiting for his turn to go there and defeat the baddie. Whereas there you have like this Trojan horse that is actually the truth, but is losing on purpose and is preventing the honest one from joining the fray because it's just 1 versus 1 at a time. So this is like this fragility, which is quite nuanced, but it's at the core of all these issues.
That is annoying.
Yeah, that is very annoying. Like the guy said the correct thing, but he lost. Come on.
Yeah. Okay. So in that case, so initially my thought process is like, why would he lose on purpose? Because if he's a self-interested actor, then he would be trying to win the game and get the incentive. And so there's no point to lose on purpose. But because he's submitting multiple claims, some honest, some dishonest, he's going to make the honest ones lose on purpose so that his dishonest one can win and maybe get a bigger incentive.
Yes, that's one way to see this. But this attack, it's just a delay attack. So the dishonest one will lose eventually because eventually it will be matched with the correct claim protected by the correct person, because the correct claim protected by the dishonest person can lose on purpose. So as soon as the dishonest one is matched with the honest one, the dishonest one will lose. So in the end, you're not able to steal the TVL of the rollup doing that. What you're able to do is delay settlement. So it's an attack on the liveness of the settlement. So maybe, I don't know, it all depends on the bonds, the stakes, but if somebody can create 50 symbols, 50 fake identities, and launch this kind of attack, they would be able to prevent, for example, Arbitrum from settling on Ethereum for a whole year. And sure, you won't gain money from the TVL.
No, but there is ways to gain money. There is ways, if I take out a short position on Arbitrum token and I know that I'm going to execute this delay attack, all of a sudden the news, oh my gosh, Arbitrum is down. What's going to happen? The train is broken. Arbitrum token dumps. And I made a lot of money because I took out a short and I knew that I was going to execute this delay attack.
Exactly. Yeah. And there are other attacks as well, like maybe this rollup, it's not Arbitrum, but it's some rollup. Maybe it could be Arbitrum, like there is a Solidity smart contract in there that controls some treasury that's on layer 1. And then this treasury is like relief funds to whatever. And if you can vandalize and prevent those funds from reaching somewhere, there are all sorts of bad behavior, which could be quite profitable, that you could do by delaying. And delaying for 1 year is like not good enough. And it's 1 year if you have like 52 symbols or something. Imagine if you have 100, it's forever. You broke the thing. You just vandalized it forever.
So what is, and I want to get into the article, but I do have of
course. But we are already getting into the article, so this is perfect.
Okay, great. So I do have a question as far as, I'm going to share the article, but then just leading into this, I want to understand which rollups right now have something like this in practice. So like, is Arbitrum currently using this fraud-proof system that does not have protection against delay attacks? Are there any rollups that currently have that type of fraud-proof system enabled? Or are all these rollups currently still using multi-sigs because they realize that the early implementation of fraud proofs is still very problematic, and we haven't seen rollups migrate away from multi-sigs and they won't until this fraud-proof algorithm problem is solved?
Yes. I'm not entirely sure what the rest of the ecosystem is doing, like currently in practice, So I think, this is just that Arbitrum is running on this previous iteration of fraud proofs that can be delayed for a very long time, but they're running that on a permissioned set of validators. And if you're on a permission set of validators, then the maximum delay that can happen is bounded. The problem is when you make it permissionless, because as soon as you make it permissionless, you open up the possibility of Sybil attacks, and their specific system is vulnerable to Sybil attacks that can delay finality, settlement.
Right.
So I think specifically Arbitrum, and look, I think, okay, I don't want to. I mean, if I'm wrong, please correct me on Twitter, but I think they have like a current fraud proof that is permissioned, because if they made it permissionless, it would be delayed forever. And that, as I understand, was the motivation for Bold is the name of their new algorithm, is to try to prevent these delay attacks. And I feel that this is quite an acceptable intermediary state. It's not a multi-sig. You have fraud proofs already. It's like, I don't know how many people are on the permission list, but it's certainly better than no fraud proofs at all. We're arguing that as we move along the decentralization of all these rollups, we also need to make it permissionless, and for that we need better algorithms.
Yeah, and so we spoke a bit about Arbitrum's bounded liquidity delay model. You're saying that in general, if we keep the set of validators limited or permissioned, then there is an upper bound on the amount of validators in the validator set. Therefore, there is a bound on how long one of these Sybil attacks could delay the settlement of the chain. And
exactly,
so it's permissioned, but it prevents a long or infinite delay. On the other hand, we have permissionless interactive fraud proofs. These are permissionless. It's very open. It's very open to new validators and more decentralized. But because it's permissionless, it means that you could have an unlimited amount of Sybil validators, and you could theoretically you could delay the settlement of the chain in ad infinitum. You infinitely delay.
Exactly. That's the perfect understanding.
Okay, so Arbitrum and OP Stack have different algorithms, and Cartesi has different. These three algorithms are the current proposals for trying to get the best of both worlds, trying to get permissionlessness, but also trying to bound the potential delay of one of these attacks.
Yes. So I think there's more criteria than that, because first, the permissionless aspect isn't just to do with decentralization. It's also to do with security, the safety of the rollup, because you can, if there are no bugs in the implementation, you can guarantee the rollup, the optimistic rollup, will function correctly because you can participate. And it's enough that one honest person participates. So the permissionless is also important, not just for decentralization, but also for safety,
Okay.
And when you consider all these criteria, it's very hard to manage all of them, you know. So specifically in the case of the first iteration of Arbitrum algorithm and our algorithm back in, I don't know, anyway, is that if you made them permissionless, the delay would appear.
Mm-hmm.
You know, you would have these delay attacks. But you could, you know, hypothetically make a new algorithm that has no delays, but it's not one of n anymore. So what I'm saying is that you have to fit all these like properties together, you know, and it's quite hard to fit all of them. You usually end up sacrificing one of them. Yeah. So
Right.
so just to say that's not just delay attacks. Delay attacks is one of the ways you could attack it. In particular, our algorithm is vulnerable to delay attacks. It's not as bad as 50 Sybil's means 1 year, but it's not good enough. And Bold algorithm, which is the new one, it's not vulnerable to delay attacks, but there are other kinds of attacks.
Got it. Okay. And so I just want to clarify real quickly, and then maybe get into like some more of the article as well as some more of the attacks. Right now, out of the 3 fraud-proof algorithms that we have here, Cartesi is named permissionless refereed tournaments. So this one is obviously permissionless. Arbitrum and OP Stack fault-proof algorithms, are these also permissionless right now, or are these permissioned?
Yeah, so my analysis is more on the algorithms themselves. And these algorithms, they were designed to handle permissionlessness.
Okay.
So they were all, yeah. So, I mean, you could, even the permissionless referee tournaments, you could take this algorithm, but then implement a permissioned system and deploy it permission. Yeah. But if we're just analyzing the algorithms, I think all 3 of those were designed to deal with permissionlessness, so that you could deploy a permissionless system, even though you could add like a permissionless on top of that, if you wanted. Yeah.
Got it. Okay. So you can, so they're an attempt at permissionless, but you could always deploy them as permissioned, and kind of handle some different trade-offs that way.
Exactly. Yeah.
Okay. So, as you said, they all have issues. They're vulnerable in different ways. We talked about Sybil attacks, which lead to this delay of settlement problem. You also state that these Sybil attacks undermine the safety and this, like we talked about, the settlement speed and or decentralization of the system. You also went on to talk about, not in the article, but just now, you talked about like there's other attacks that these systems are vulnerable to. Do you want to say maybe just a quick word, or I can scroll down in the article, as to what are the other attacks that these systems are vulnerable to that are not the Sybil delay that we spent most of the time today talking about?
Yeah. So they're all Sybil attacks, but they compromise different things. So one of them could compromise the liveness, you know, like the settlement speed. But another could actually compromise the safety of the algorithm. So they're all Sybil attacks, but they compromise different things depending on which algorithms we are analyzing.
Got it.
Yeah.
Okay. Got it. So they're all different types of Sybil attacks that break different pieces.
Yes, exactly. And the criteria that I propose, you know, so I invite everybody that's like watching, listening to read the whole discussion, try to contribute to it. So this criteria, there were a few concerns raised, I guess, you know, or disagreements raised. And maybe they were not precise enough. So maybe we'll try to go again, because there's some nuance to them. So we all want the algorithm to be permissionless. So let's put that as our assumption. You know, like everything that we're analyzing is permissionless, and we want a permissionless algorithm to be and then safe. And by safety, what I guess I meant there on the article is that it keeps the one of n assumption of fraud proofs. So I'm considering something like a fraud proof algorithm safe is if one of n is enough to enforce the truth.
Okay.
So I could just rewrite safe by one of n. I think it would have been a more precise naming.
Mm-hmm.
Then the second one, I call it promptness, settlement speed. It's how long you can delay it. Yes. Okay.
And
yeah.
And decentralized, if validating doesn't require a lot of resources like hardware and funds. Now,
yes, because you could set. So there are mainly three kinds of resources that you need to have to participate in these games. And these resources are bonds, stakes, collaterals, so that's one. The other one is block space. You need to have gas to pay for like transaction fees, and you need hardware. So those are the three resources that somebody needs to have. Now, if you set the bond value to be like $1 million, $5 million, you may gain more like safety or more promptness, depending, but then you're sacrificing on this axis that I'm calling decentralization, because, I want to be able to go there and validate some chain and then enforce the truth. But if it's cost me like a fixed 5 million, then you start losing on this idea of decentralization.
And permissionlessness. It's almost
exactly
like a barrier to entry, which means that the system itself is less permissionless than anyone and everyone.
Exactly.
Because not everyone can overcome those barriers to entry. Now, I realize that decentralization is a spectrum, because maybe there has to be some sort of resources required.
You do, yeah.
Similarly, promptness. If we're thinking about the delay attack again, obviously, if we have to settle and settle is not a great choice of words here, but if the delay is 10 minutes, that's much, much, much better than a delay of 1 year, but it's still a spectrum between 10 minutes and 1 year. There's a lot of middle ground where something can be more or less prompt than something else. The first example here, safe, I would argue that this is binary, because and I would say that these promptness and decentralization are more of a spectra, as you say here. But because we rely on the one of n assumption, I would argue that the safe property is more binary than not, because it is expressing that if you can remain in this one of n system and still enforce that fraud proof, then you're considered safe. But as soon as you get into 2 of n or worse, then you start getting less safe. Or
yes.
So I would say that maybe safety is a binary property, while promptness and decentralization are spectra.
Yes, I would agree with that. Yeah, like we could try to frame a more like we could set different criteria, but the way I'm arguing there, I would say that it's binary. Yeah.
Okay. Again, constructive criticism, just how I'm reading. Okay, so that makes sense. I think those are very virtuous properties that a fraud-proof system ought to have. And we say in an ideal world, we want the honest validator to win any dispute in a timely manner using nothing more than a toaster. I love that, because it represents like the low resources required to run a validator, very low barrier of entry if anyone can run it with a toaster.
Yes.
And it also represents the one of n safety property, because even if there's just one honest toaster in the world, if that toaster can win, then it means that the honesty it prevails and it's safe. and in a timely manner. And I think that demonstrates the promptness property, which is very much a spectrum. Okay, and then in this case, we say that the honest validator, the honest toaster, is our hero, and then we have a set of dishonest validators. Sometimes, and we talked about kind of like the worst villain or the best villain, which we call the adversaries, these dishonest validators. Okay, so now I think we've set the scene. I want to take a quick tangent, actually, because I had a realization. I'm not sure how accurate it is, but when we were talking about this splitting, to play this game, we have two. Let's just take the case where we have 1 against 1, and we have an honest toaster against a dishonest toaster. And we have this game where we say, okay, you disagree. These two validators disagree. Let's cut the game in half. Let's look at the middle, and we say, do you disagree here? Yes or no? And then we cut in half again. Do you disagree? And we cut and we cut and we cut until we get a single state transition that we can prove from one to the next. Now, this reminds me a lot of data availability sampling. Because we're sampling different pieces of the, we're checking different pieces of the of the validators and whether or not they disagree. In the case of a block, we're checking whether or not there's any missing data, and we're making sure that all this data availability is available. Is this like a similar mechanism that we're seeing DA solutions like Celestia, EigenDA? There's a lot of DA solutions out there right now. But is this data availability sampling process of splitting and cutting and sampling, is that a similar process to the game that we described to resolve disagreements between honest and dishonest validators?
Yeah, I don't know, actually. So this cutting, it's from a class of algorithms that we call divide and conquer algorithm. I guess you could call it divide and conquer, where you just really like splitting, and at each iteration of the algorithm, you reduce your search space in half. So the first cut you do, you throw away half of the search space, and the second cut is always half. So this is called like a binary search. Where if you like the binary search, more like a standard presentation of it is, if you have a sorted list of elements, you can quickly find any element in this list by doing this cutting and splitting. You check the middle. Is the middle larger than what I'm searching for? If it is, it's on the first half. It's not, it's on the second half. So sampling, I'm not sure if it's exactly the same algorithm, like I'm not a specialist on it. The way I understand it's more like random, I tell you, look, give me this, like you roll a die and then you say, I want this one. The other person cannot guess what it is. Otherwise it would be able to like game the system. Yeah, that's my interpretation, but I don't know.
Okay. I may be reaching for that connection because, in my mind, I come from a math background, and I'm remembering like my 11th grade calculus teacher teaching me how to take an integral with a Riemann sum. And what you do is you have the curve, right? And then you just chop the area under the curve into very small rectangles. So you chop and you chop and you chop and you chop. And there's the formula where you take h that is equal to the number of rectangles. And if you have h to infinity and you just keep like compressing these rectangles until they're like infinitesimally small. And then you're able to basically estimate the area under the curve with like exact precision because you take the limit as the rectangles go to infinity. And so they just both of those algorithms feel very much like a Riemann sum that we take in the data availability case for the data in a block by sampling and cutting and sampling and cutting. And then in this case, again, like cutting, checking, cutting, checking. So in my mathematical mind, trying to draw a connection there, maybe it's there, maybe it's not. I might be seeing things, but Okay, that was a tangent. Let's get back on track. So we have these three properties of a good fraud proof. A good permissionless interactive fraud proof is safe, prompt, and decentralized. And the goal here is to solve the question or play the game of hero versus adversary, hero being honest validator, adversary being dishonest validator, and resolve this contradiction or this disagreement between honest and dishonest validators. And so a lot of this is dependent on the incentives. And there's bonds and there's resources that it takes to run a validator, and then also to kind of like why you would want to play this game honestly or dishonestly. So talk us through what's at stake a little bit and why incentives are important.
Yes. So I'm going to take the problem of incentivizing people to validate. You want to get like, for example, on Ethereum, if you deploy a smart contract, it's going to work as long as Ethereum is working. You kind of don't have to worry about it in a way, because you're trusting the security of the whole network. Now, if you are relying on a one of n assumption, the best security you can have is you going there and validating it. And you could, say that there are many reasons to do that, because you have maybe $1 million locked in that rollup, and a laptop is much cheaper than that, so you're going to run it. Or you could have like, I don't know, you're playing like a MMO RPG and you have like this super high level character that you want to be there, existing. So there are many reasons for why you could have one honest person validating it. So I'm going to just put that as an assumption. I'm going to assume there already is one honest validator who is interested in protecting the chain. So let's keep that as an assumption and now talk about the overall system. Now, if you're talking about a rollup which has a lot of money, like a lot of like TVL, and there is a way to exploit the system and steal the whole TVL, I think it's a reasonable argument to say that somebody would be willing to burn, I don't know, a few billions if they stand to win like tens of billions.
Yeah. We spoke a bit about like the potential, even if you're not able to take the TVL from an application or a chain. We talked about like there is profit to be made from just shutting a chain down. If I have a short, there's news, oh my God, this chain is down. My short is going to be profitable. I'm like that. There's going to be poor news, poor sentiment, selling. And so there is a lot that an adversary could make, even if they're not directly rugging and taking the TVL from the network. They could take out short positions and generate financial incentives that way.
Yeah, exactly. And so there's opportunity in a delay attack, and it's all of that, like a short position, and certainly many others. And there's also, I think, a different kind of winning, which is if you can compromise the safety and actually rug the TVL, then I think it's actually possibly an even larger winning, because as you said, maybe you could short it and a delay would make you rich. But if you could rug it, you would be rich both from the short and from the TVL. So I think the point that I was trying to raise on that section, which was quite contentious, by the way, is that to me, it's reasonable that if somebody can win 10 billion by burning 1 billion, it's a good exchange, So if there is a safety, if there's a way to compromise the safety of the system by burning $1 billion, it's reasonable that somebody might do it.
Yep, that makes a lot of sense. Okay. So now you go on to kind of explain Kineti. Like, who is Kineti, and just at a high level, what is the work that set the stage for these concepts?
Yes. So fraud proofs are actually quite an old idea. I think the first iteration is like maybe from the 90s, I think, from Page, I think. So, I don't know. And then there's Kineti, which is, I guess, the more modern version of it. That's an author, like the et al. Is like the list of all the other authors. And they offer a very good improvement on the fraud proofs from the 90s by adding Merkle trees. So if you Merkleize the state, you can actually make. So instead of imagine you said like the board of chess. You have to put the whole board on chain, and then when you make a claim, you put the whole board, all the positions. Now imagine if it's not chess. Imagine if it's something like really huge. You don't want to have to put all of that on chain. So using like some very clever cryptographic techniques, using Merkle trees and stuff like that, you can actually just put Merkle root hashes on the blockchain, and then you offer a few Merkle proofs, and you're able to run a state transition function on top of just Merkle root hash of the whole state if you're given enough Merkle proofs. So I think that's like the fraud-proof work that we are all based on. So that's like it's more like introduction to how it works, giving some context because it was important to explain the next algorithm. And yeah, so essentially on that section, I think it's explaining what I just said, the binary search. And then once you find the divergence, you apply like the state transition function. And then also the other paragraph is like, if you try to extend this algorithm to many players, then you run on this delay attacks. I also talk about the fragility, that very annoying fragility. Yeah.
Always annoying. But hopefully we'll get to a solution. And yeah, this makes sense. So here, this is basically the chess example.
Yes.
But stay just in the computer computational terminology. But this is basically the chess game with two players. And then this is your extrapolation to many players, more so in the Ethereum world, where we have a permissionless set of validators. That would mean many players. And then so you mentioned that Kineti proposes a few ways to make verification games with many players, and takes this fragility into consideration, that annoying little fragility. And then this is what the permissionless interactive fraud proofs, that Cartesi, Arbitrum, like these are what the algorithms are now based on. And so this Kineti is kind of like the preliminary knowledge and research that has gotten has kind of like set the stage for these new algorithms to come forth and try to solve these annoying little issues.
Yes.
Okay. So yeah, please continue.
Yeah. So the first issue to solve, which is a very annoying little issue, is that somebody could tell the truth and lose on purpose. So you in the end you claim the correct final state, like the chessboard. You put all the pieces on exactly the right places, but then you play the game dishonestly and lose on purpose. Now, what does it mean to play dishonestly? So as you said, like the referee, the blockchain, Ethereum, it asks what was the state in the middle, and to see if the two agree or disagree, right? Now, the dishonest person playing dishonestly but claiming the correct thing, they could lie. They could say, oh no, actually, I disagree with this, when in fact they should have agreed, or vice versa. They should have disagreed, or disagreement, they should have agreed. So during this binary search, that's the fragile portion, because you could lie during the whole process in a way that the divergence doesn't fall on the real divergence. So it would appear the person who claimed the right thing is in contradiction. So, so that is like the annoying part. So we introduced something that we call computation hashes. And computation hashes are a change on the claim. So instead of you making a claim just about the final state, so the claim is a commitment to the final state. Instead of you just posting a commitment to the final state, you post a commitment of the entire path of the computation. So every intermediary step, every intermediary board configuration, you also post a commitment of that along with the final state. So it's actually a Merkle tree. So we put every like intermediary state, Merkleize it together, and then we post a single claim, which is the whole path instead of just the end.
And so do you post this to Ethereum?
Yes.
Okay. And so like part of my understanding of like this Ethereum centric roadmap, you know, that we opened up the conversation with was that we're moving computation off chain or off of layer one in order to save the computational resources of the layer one itself. And then we're going to post some sort of proof verification back to the layer one. Now, that to me says, okay, let's do the whole Merkle tree path off layer one on a rollup, and then post the Merkle root for that tree and settle that root to Ethereum. Is it counterintuitive or counterproductive to then take that entire tree and post the entire tree to Ethereum? Does that contradict the problem that we were trying to solve originally?
Yeah. So before, you know, if you just look at like the Kineti approach, what you put on chain is just the hash, the state hash of your rollup. So you don't put the board, you put a Merkleized, you know, version of the board. So it's just a hash that you post. And also on the Kineti, on the way everybody does this, is that the whole fraud proof, if it happens, of course, you know, it only happens if there's a disagreement, is already fought on chain. So the change that we're making is that we're changing what a claim is. It's still just a hash, but this hash now represents a different thing.
Now it represents the tree.
The whole path, exactly.
The whole path of state transitions from initial state at the beginning of the epoch to final state at the end of the epoch.
Exactly.
Okay.
Yeah, and it's actually a nested Merkle tree because the leaps, which are the intermediary states, they're also Merkle roots of the state of the rollup, you know? So, so we have the state, you Merkleize it, that's a single intermediary state root hash. And then you grab a set of them, and then you make a second Merkle tree. So it's like two Merkle trees nested one inside the other. They don't have this. Yeah, go ahead.
Is that not too computationally intensive?
It is. It is quite intensive to the point of being prohibitive. So there are other techniques we have to add. So I think first, just to understand how it works, we can assume it's not prohibitive for now. And then we go, no, it's actually quite prohibitive. And here are a few strategies to deal with that. So if you can build this computation hash, that will be the prohibitive part. But if you can build it and you can claim it, now when you make the bisection, when the blockchain asks what's the state in between, you can't lie because you committed to that. So you go there and you post a Merkle proof saying, no, in the middle, I committed to this specific state. So you can't lie anymore. So if you can't lie, what this means is that there is only one valid computation hash, and nobody can lose on purpose anymore. So the previous algorithm, it revealed liars, not lies, because you could have the honest thing losing on purpose. So it just revealed liars. So now there's this shift in that computation hashes reveal actual lies instead of liars.
Got it. Because we can pinpoint the transition in the path
Yes.
that is in disagreement with someone else's state transition.
Yes. Yes. So we are making a more robust commitment. We're making not a commitment just to the final state. Since we make a commitment to the whole thing, you cannot dishonestly lie about what was in between. Because before, the fragility is because you could lie about what was in between. Now, because you committed to that, like you pre-committed to that, you can't lie anymore. Otherwise, the proofs won't match.
Got it. Okay, so these permissionless referee tournaments include these computation hashes, which solve that. Finally, we solved that little annoying thing where someone could lose on purpose. Okay, so that sounds great, but this solution is somewhat problematic because it is a much more robust claim to settle the entire path of the state transitions from initial state to end state. And so we have to make sure that this is not prohibitive. And so how do we solve, we solve one annoying little thing and it leads to another annoying problem. So how do we solve the problem that we've now created?
Yeah, so when designing algorithms, it's always like this, like, oh yes, finally I solved this. And then you see, oh no, there's this trade-off, it's really hard to get everything together better, So first, by solving this annoying thing, we can do exactly what you proposed before, which is setting up these tournament brackets, Before you couldn't do the tournament brackets because it was a dispute between players, not between claims. It matters who made the claim because the algorithm, the previous one, worked by finding liars. So you need to know who's the liar, like who is the person behind each claim. Now we don't need to know that anymore. So there's only a single honest claim. There are not multiple honest claims and they're different because they were made by different people. No, now this here is only a single honest claim. Everybody can join together behind it. You don't need to sign the messages and check who's sending the transactions. So this allows us to build this tournament bracket style that you described before, which you go eliminating half of the symbols at each bracket level. So you're essentially making the adversary who paid a lot of money to create those bunch of symbols, and then you're making the adversary kill his own symbols himself. So that's the approach, the mechanism by which this can improve.
I love it.
And then there is the question that you raised, okay, that's all beautiful, how do you build the computation hash?
Mm-hmm.
There are two strategies. The first strategy that is actually quite clever, it was, when you feel clever, that's one such case of feeling clever, which is instead of making a commitment to the whole path, each and all intermediary state, step by step, you create a sparse commitment. So instead of being 1, 2, 3, 4, 5, you go 1, 10, 20, 30, So you put a stride in between each leaf of this Merkle tree. And once you do that, it means that you can't do the step anymore. You can't do the state transition function. Because now if you find the divergence, I gave an example of 10, stride. It's 10, it's not 1. You can't do a one-step proof on something that's 10, However, once you find the divergence and you rule out everything else and you reduce it to just these 10 steps, you can recursively use the same process, but now require a commitment that includes all intermediary states. So arbitration call this a refinement. That's a good name. You could call it this sparse commitment that becomes denser as you go in. But the overall idea is this: you have like a permissionless referee tournament on the top, and each match can create a recursive new permissionless referee tournament, but with a smaller range of computation because you ruled out a lot of it, and now you can make a more dense commitment, and you keep doing that until you reach something that's comfortable, So we are looking at 2 to 3 levels of nested tournaments. Like with good engineering, we can probably reduce that to 2. Our benchmarks are like indicating that we can go down to 2. But, okay, so you have these 2 levels. That's very nice. You make, on the top level, a very sparse commitment that the cost of building it is kind of negligible when you compare it with the cost of just running the computation. But it makes the settlement speed significantly worse. So if just one level, if we could build the prohibitively expensive thing, this would settle in like logarithm time. In 2 levels, like logarithm squared, which is not good, Like logarithm, in this case, is already not good enough because the constant is very high. It's like a week times the logarithm. But then if you do a week times the logarithm square, that's not good. Yeah. So now we like, oh, okay, that's very clever, but it's slow. Let's go back to like, how can we build this prohibitively expensive thing without doing this nested recursive thing? And the solution we got is, well, we can use just on this point a ZK proof. So you actually make a commitment which it looks sparse, because you're jumping like, 1 million instructions in 1 million instructions. But now the one-step proof is no longer a single step, like RISC-V on our case, RISC-V step. It's like 1 million RISC-V steps. And we can build a ZK proof from that. And the blockchain can validate a ZK proof of that cheaply. So we can do everything on a single level, without having to go through these recursive multi-stage disputes, which is what I said. Exactly, right.
Yeah. Yep. It makes sense. I mean, you talk about how this gets us into logarithmic time, which is great, but because we recursively nest each of these dispute games, it means that we're almost raising the settlement time to a power, whether it's 2 or 3 or 4, depends how many times we have to go deeper and deeper and deeper into this path. And so you talk about that in this trilemma here, that we can increase the stakes, but it creates that barrier of entry. I mentioned that at the beginning. We could reduce the base layer censorship, which is good for promptness and decentralization, but we lose that one event safety guarantee.
Yeah, just say we don't exactly lose it. So our model is, we model the blockchain as being, we model the dishonest actors as being able to delay, like really censor your transactions on layer 1 for up to a week. So this 1 week is kind of like this folk, like knowledge, wisdom that everybody's using, like, oh, a week, we consider it safe enough. So that's what we're using. Yeah.
Yeah, but what if like Optimism and Arbitrum, these optimistic rollups, just arbitrarily chose, like, 7 days is actually harming like some of these fraud proof mechanisms? Why don't we cut that down to about 3 days?
Exactly. So you could argue that this weakens the security of it. Personally, I think 7 days is way too extreme. I think 3 days is probably something, more manageable. Yeah, so that item in the middle is exactly what you said. Like, oh, wait a minute, 7 days is way too much. Let's do like 3 days. But this you could argue that it harms safety, but since we in this conversation already established that safety, we're just considering one of n, then it wouldn't harm the one of n. But we need to set that to some reasonable time.
Mm-hmm. Okay, got it. And that's what you mean by safety, harming safety in this promptness and decentralization one. If we reduce the maximum base, what does the maximum base layer censorship mean?
So this is the 7-day. So
okay,
because it's curious. I've seen people claim that if you have the reason it's 7 days is because you need to send 50 transactions to the blockchain. Mm-hmm. And we've estimated that you can put 50 transactions on the blockchain in 7 days.
Okay.
And the 50 is that bisection game that you play, like the cutting. Mm-hmm. You have to cut it, 50 times, something like this. Mm-hmm. But this is not how we model the censorship, mm-hmm. model of Ethereum. What we model is there are two regimes under which the adversary can switch. So there's a standard regime, which is like the normal Ethereum one. And in the standard regime, we can actually send 50 transactions. We don't need 7 days to send 50 transactions. We can do that in less than a day. Probably could do that in 1 hour, I guess. Mm-hmm. But we have to consider, but if we set 1 hour, this means that if an attacker can censor the single honest participant for 1 hour, they would win.
Like by pumping up the gas costs too high so that they couldn't get a transaction.
Or just bribing block attesters to not attest any block that contains a transaction. It's very expensive to carry that out.
Right.
But for an hour, maybe you can do it. Mm-hmm. So we consider these two regimes, and one of them is the censorship regime that adds up to a week. Mm-hmm. So what we do is, if we can reasonably send 50 transactions in, 3 hours, 6 hours, then we must give 6 hours plus 1 week. If we reduce the number of transactions to instead of, 50 to 25, then we reduce the 6 hours to 3 hours, but we still keep the 1 week. That's to say that non-interactive fraud proofs, I think like the original OVM, I'm pretty sure it still had a 1 week challenge period, even though you could think that once you raise the flag, it's okay, like it's one transaction instead of 50. Yeah. I think that's a bit complicated, just.
Yeah.
Okay. Yeah. I think your original understanding is good enough. Yeah.
Yeah. Once we start changing the 7-day window, there's arguments for both sides on why that would help some things, but it would potentially harm safety, which is kind of the trade-off that you mentioned in the second bullet point.
Exactly. Look, I think 3 days is probably good enough, especially if you're considering like small change, like if it's a small roll-up that's doesn't have billions in TVL. Mm-hmm. 3 days might be good enough, but I chose the
industry standard 7 days.
Exactly. So, and because the others are also geared to large TVL, so I felt that the analysis would be more like apples to apples if we tuned these parameters to match something with high TVL in mind.
Mm-hmm. Got it. Okay.
Right. So that's So in this algorithm, you can tune it to it's like a trilemma. You can tune it to sacrifice one of the three of them.
Mm-hmm. And
we
the
chose
final,
that specific one. Yeah.
Got it. And the final bullet point is the logarithmic time that the delay grows by based on the number of Sybils.
Yes.
Okay. So that is still quite slow, especially when we start nesting these disputes. But then you use ZK proofs as a way to a way to avoid this promptness issue, where if you were to nest 2, 3, 4 layers, that would grow the delay by 2, 3, 4 times, but you have a way to avoid that growth in the delay by using ZK proofs.
Yes. So,
Yeah.
and just say that this is still an interactive fraud proof. We're just changing, like it's like an implementation detail. We are changing just the state transition function to internally use ZK, like it doesn't turn into a non-interactive or to a ZK rollup. It's really still an interactive fraud proof. It's just that our state transition function now executes a huge chunk of steps instead of a tiny little step. And this huge chunk of steps, I shouldn't have said huge because our benchmarks were doing like 1 million steps. And the reason was 1 million. So this is all the trade-offs, we want to keep the toaster property, and maybe if we add like a super toaster, like a GPU farm of toasters, then we could probably do like, I don't know, several million transactions, like cycles, CPU cycles. But we wanted to be able to do this on a laptop with one GPU, like just one GPU. So we were considering what can a laptop with one GPU do in an hour in ZK. And our like very old benchmarks were hitting like this 1 million. So this means we can make our commitment skip 1 million in 1 million state root calculations. So we can make this like 1 million steps sparse. And now the work is really trying to optimize this as much as possible because all these ZK VMs are becoming much faster. So maybe we can still do in an hour instead of 1 million, 2 million. And also optimizing on our end because maybe we can do more like denser commitments in a shorter time.
Got it.
Yeah, I think the main takeaway of all of this I said is just that it's still a fraud proof.
Mm-hmm.
Still an interactive fraud proof. Just because it uses ZK.
Yeah. Despite the ZK state transition function.
Yes.
It's still an interactive fraud proof.
Exactly. Yeah.
Okay. Okay. And then and that's Cartesi's implementation. And then you go on to describe a little bit more about Arbitrum's bonded liquidity delay model. And then I imagine let's see, do we get into like OP? We talk about variant 1. We talk about variant 2, which is different attacks. The first attack on the computational resources of our honest toaster. The second, an attack on the honest toaster's block space. And then the third on the funds. And these are all different ways to prohibit the honest toaster from entering either permissionlessly or winning the dispute resolution game.
Yes. So one way to call this is like a resource exhaustion attack. So you create a bunch of symbols, make our hero toaster have to respond in kind, and just exhaust their resources until they can no longer participate in this game.
Got it. And
go ahead. Yeah.
Is this set of exhaustion attacks, is that different than the Sybil attacks that we talked about? Well, actually, I think I answered my own question because these all fall under Sybil attacks, but there's different types of Sybil attacks. Some of them are an attack on the liveness of the chain and the time that it takes to settle the chain. We call those delay attacks. And then we have another subclass of Sybil attacks that are these exhaustion attacks that try to exhaust the the computational resources of our hero toaster.
Yes, not only the computational resources, but also like funds, like their capacity to pay for bonds and their capacity to pay for gas.
Mm-hmm.
And this kind of Sybil attacks. So you have this class of attacks, which is like Sybil attacks. And now this specific one, it compromises the safety of the algorithm. So this one isn't like attacking the liveness anymore. It's actually trying to steal the TVL.
Yep. Okay. And then again, we leverage ZK proofs at the state transition function to eliminate some of these challenges. And so it seems like a lot of the suggestions made in this post are to implement the ZK proofs at the state transition function as a way to prevent in the first example, Cartesi's algorithm, as a way to prevent us from going too deep into these nested tournaments. And then
Yes.
in the Arbitrum example, a way to eliminate some of these exhaustion attacks.
Yes, but the mechanism is very similar to Cartesi because Arbitrum also uses computation hashes.
Mm-hmm. Okay.
And they also use this strategy of nesting their dispute game. So I think their current aim is at 3 levels.
Mm-hmm.
So when you nest it 3 times, you really open up this vector of attack that allows you to expand the hero toaster resources.
Mm-hmm.
So just like our algorithm that we really want to make it single level, if bold is made single level, it also fixes this extortion attack that we described. So I wouldn't say that all of the suggestion is to use ZK here and there. It's just that bold and our algorithm, they use very similar techniques,
Mm-hmm.
but similar techniques, but different in very important parts. But likewise, they are also vulnerable because of nesting tournaments. And if we can unnest them by using like a ZK proof on the state transition, we can really improve a lot of their safety issues, or in the case of Cartesi, liveness issue.
Got it. Okay. And so just one more time, you said it's not just that we're implementing ZK proofs at the state transition function. What is it that separates this implementation from some of the previous ones that have been theorized?
So what's the difference between? I didn't get the relation between ZK yet.
Sorry, I think I just zoned out. I think I just didn't hear the explanation where you started to say that it wasn't just about implementing ZK proofs here and there. There's more.
Yeah. So, like you said that it seemed that the solution was to use ZK here and there, right? Because we just saw 2 algorithms, and the 2 of them had, let's use a little bit of ZK. But the reason both of them had this, let's use a little bit of ZK, is because they use similar techniques of this computation hash, and then this nesting, this recursiveness creation of disputes. And this recursion, in case of Cartesi, creates a liveness problem. And in bold, it creates a safety problem. So if we could unnest them, and one way to unnest them is to use ZK, then you really improve the liveness in Cartesi, and you really improve the safety in bold.
Awesome. Okay, that makes a lot more sense. Thank you for reiterating that. And then, okay, so the solution was to unnest these resolution mechanisms for both bold in Arbitrum's case, and then the permissioned tournaments, the permissionless referee tournaments in Cartesi's case. The solution is that there's a lot of issues by nesting in these tournaments for liveness and for safety. So if we unnest them, we can solve those issues, and the way to unnest them is with ZK proofs at the state transition function. Now,
yes, but
mm-hmm.
it's still not good enough. It's like a major improvement, but still not good enough. So we want, I guess, we want to kind of like finish our conversation in this like happy tone, like, oh, the solution is doing X, Y, Z. No, there's no solution yet. I don't know what is the solution. I know how we can get there, and how is first agreeing upon all the problems we have, and all of us in the industry, in the ecosystem, trying to come up with something better.
Mm-hmm. Yeah. And that's why this post is generally a call for constructive criticism and to try to shed some more light. But first, agree on some of the first principles and the premise, and then start to extrapolate from there, like what some other potential solutions we could implement. And so OP Stack's fault-proof system, does this also have a similar nesting type of mechanism?
No.
Okay.
So it doesn't use computation hashes.
Okay.
So you just claim the final state, and then you kind of go like bisecting, doing that cutting that you mentioned. But you allow multiple people to do the cutting. So I could go there and claim the final state correctly, and and then the adversary goes there and makes his like cut, and then I go and make my cut. But then somebody dishonest could make the same cut I did, but dishonestly. It will be that fragility that we talked about. But on Optimism, they created this clever data structure, this like graph, a DAG, that allows multiple people to bisect, and then there's a way for you to counter the wrong counter. It's it's getting more on the details on how it works, but the idea is that it allows anybody to go there and make a bisection.
Got it. Okay. And you mentioned that all of these dispute games are played simultaneously, which makes the dispute finishing constant time. That's better than logarithmic time, right?
Yes, that is better. Yes.
Okay. And so the settlement of these dispute games is faster, but I have a feeling that we are still not going to like find a happy solution. So what is the problem? What is the problem with the way that Optimism has implemented their fraud-proof system?
Yeah, so it is a very similar problem as the one involved, the resource exhaustion. So if the attacker is better funded, the adversary is better funded than our hero toaster, the hero toaster will lose. So that's and this ties back to what I said, like I'd be willing to burn, I don't have $1 billion, but I'd be willing to burn, if I had, I'd be willing to burn it to get 10,
Right.
So it is a very uncomfortable position to be in, like having an adversary that's possibly quite well funded and requiring the hero toasters to have the same amount of resources. And this violates our 1 of n, because now it's no longer 1 of n. It's a bit like Ethereum, like Bitcoin, like you need to have a percentage of the overall honest resource. So I don't know, like in Bitcoin proof of work, you need like 50% of the hashing power, or rather the set of honest Bitcoin validators need to together have 50%.
Like this.
And we want to be 1 of n. We don't want to be half of n. We want to be 1 of n.
And in this case, N is the total amount of computational resources amongst all of the validators. And so the honest validators would have to have 51% of the capital, the stake, or the mining hashing power in order to win this fraud-proof game.
Exactly. And in this case, the resources are computers, as you said, like hardware, also like gas fees. And this is the last one is the hardest one, the bonds. So if we just consider the last one, then if the adversary can pay for more bonds than the hero can pay for bonds, then the adversary will win.
Yep. This makes a proof of whale even more profitable for the adversary. Basically, and proof of whale is basically like they can prove that they have more computational or just more resources in general. The whale can prove they have more resources and therefore win the fraud game.
Yes. I mean, proof of whale, I admit, is a bit of like a facetious, way to call this. But it's essentially that, like if you have more resources, you can break the thing. That's why we chose like proof of whale. You can essentially prove by playing in a very specific way the game that you have more resources than everybody else and win.
Mm-hmm. And so we're left with this conclusion where we have this trilemma of safety, promptness, and decentralization. And so we talked about the permissionless referee tournaments. It does well, but it's still not great. Bold, in Arbitrum's case, again, makes these trade-offs. You made some improvements to the safety property of bold, and we call it bold plus plus, but it still is not perfect. And then once again, the OP implementation is still problematic in certain characteristics when it comes to proof of whale attacks. And so we're left at this slightly less annoying situation where we've kind of addressed like the problem in the room, and we've kind of like called out what the issues are with each of these different design choices, but still we're left with this trilemma that has no perfect solution yet.
Yes.
Okay.
So I just want to give some more detail.
We won't get too deep into the comments, but please go ahead.
Yeah. So just like for full disclosure, both bold with 3 levels and optimism, they're both vulnerable to this proof of whale, which means it's not one of n, but it also indicates that the bold performs better because it's not 50%, it's like 10%. So whereas it seems that in the optimism case, if the attacker has 51% of the resources, they're able to win. It also seems that in bold, the attackers need instead 91% of the resources to win. So I mean, it is an improvement, like we are. Yes, exactly. But I would argue that what we really need is one of n. It's like it doesn't matter if it's you against the whole world, the whole universe, like this horde of dishonest toasters, like just stumbling around to try to fuck you up. You must be able to win alone. And I think that is the standard that we should set for fraud proofs. Now, obviously, if it's 1% of n, that's very good. That's better than 10%. That's better than 50%. If we can reduce that, that is certainly an improvement. You could argue that for some networks, that is safe enough, especially if it's a network like Arbitrum or Optimism, because like this huge roll-up of a lot of TVL, they could probably keep like 1% of like these resources like locked in a bank just waiting to protect against the whale. But I think as we try to design it, we should try to design something that is one of n. Maybe we have to sacrifice it to get the other things. And if we sacrifice it, maybe we can sacrifice it in a way that's like 0.1%, instead of 10% or 50%. But in the end, this is really like this like we need to talk about fraud proofs moment. I think we don't have an ideal solution yet. And we need to, I think, all agree that we don't have an ideal solution yet. Because once we agree, we can start working on the new solution. And I hope we can start working on the new solution together.
I hope so too. I'm looking forward to almost like some new conversations, right? I think this was perfect to lay out what the current situation is. We identified pretty much all like the general trade-offs that the current design choices make, the issues with each of those design choices. And so I tend to agree the next step is going to be to get some agreement, make sure that we didn't miss any of these problems with any of these solutions or any design choices that are also worthy of being in this conversation. And then we can start to make progress and we can start to push forward on how to solve these with the least amount of trade-offs and
compromises. Yeah.
The least amount of compromises. Exactly. And hopefully come to a better solution that all of us are able to go and we can run with and we can implement in different cases.
Yes. And I'd also like to mention that we had replies, so there was an engineer from Optimism who says, look, I work for Optimism, but these are just my opinions, but he answered and he quite engaged honestly on the conversation. And Ed Felton posted the new paper that they had. So since the post was made, they updated the paper, which included the resource exhaustion angle, analyzing all the risks that it poses and everything. So that's also like engagement. So I am quite optimistic that we will be able to form some sort of cooperation because I think it's already happening. And I would like to thank the other projects that are really like on board with this.
Amazing. Yeah, it is really it's really helpful to see the constructive criticism, the comments, the engagement from the projects that are mentioned in the research post. Gabriel, this is probably by far the longest video on the channel.
Wow. Yeah. We should hear you.
Yeah.
No, thank you. This has been very good, very pleasant, and informative.
Thank you so much for the time and for explaining fraud proofs all the way through to the current landscape of fraud proofs that we see today. Thank you.
Thank you.